Welcome to the deep dive. Today, we're plunging into software. You know, that invisible stuff running pretty much everything digital.
It really is everywhere.
Yeah, so we've pulled together a ton of information, and our mission today is to give you a quick, but really solid understanding of it, where it came from, what it actually is, why it matters so much, without getting lost in the weeds.
Okay, let's dive right in then. So software, at its core, is basically the set of instructions, computer programs that tell a computer what tasks to perform.
Simple enough, yeah.
Well, yes and no. It's not just the code. It also includes things like the design documents, the specifications, basically the blueprints for how it's built and supposed to work.
Like the whole package. And it's always been around, has it? The term itself is relatively new.
That's right. Software, as a word, apparently was coined by a mathematician, John Wilder Tukey, back in 1958.
Huh, 1958. But
Yeah.
people were programming before that, surely.
Oh, absolutely. In the late 1940s, they were programming directly in machine language, raw ones and zeros, essentially.
Sounds like a real headache.
It was incredibly difficult, very hard to debug, find errors, and it was totally tied to the specific computer hardware. Not portable at all. A massive bottleneck, really.
So what changed?
Around 1958, actually, we saw the first high-level languages emerge. Think Fortran, Lisp, COBOL. These were, well, revolutionary. They were
Yeah.
much easier for humans to read and write. And crucially, they were portable. You could run the same code on different machines, more or less. This massively boosted programmer productivity.
Ah, so it shifted the focus. It wasn't just about the hardware cost anymore.
Exactly. People realized the human element, the programmer's time and effort, was becoming the bigger constraint. And we should mention the integrated circuit arriving was fundamental. Couldn't have modern software without it.
Makes sense. Okay, so when we say software, are there different basic kinds we interact with?
Definitely. Broadly, you can split it into two main camps. First, you've got the operating system like Windows, Mac OS, Linux. Its job is managing the hardware, providing the basic interface, offering services for other programs, kind of the stage manager.
Okay. And the second?
Application software. These are the programs you use to do specific things, word processors, web browsers, games, you name it. And actually, applications make up the vast, vast majority of all software.
Got it. And how we get this software has changed too, right? It used to be all boxes and CDs.
Yeah, that was the traditional on-premise model. You bought a license, often perpetual, installed it on your machine.
But now,
Now, especially with the internet, software as a service SaaS has really taken over. The software lives on the provider's servers and you access it online, usually paying a subscription. By 2023, that became the dominant model, especially for businesses.
okay, history, types, delivery.
Mhm.
What about making the stuff? It's complex, I imagine.
Oh, absolutely. It's a whole life cycle. It starts with figuring out what it needs to do, the requirements. Then you design it, write the code that's implementation, test it rigorously, release it, and then the big one.
Maintain it.
Maintenance is the big one, more than building it. Often, yes, that's what surprises people, over the entire life of a piece of software, maintenance fixing bugs, adapting to new operating systems or security threats, adding small features can easily be the largest chunk of the cost.
Wow.
And the whole process has challenges. Estimating effort is notoriously tricky. And you need way more than just programmers, designers, testers, project managers. It's also, well, pretty common to release software that isn't perfect.
So bugs are expected.
To some extent, yes. Which is why that post-release maintenance is so vital. The environment software runs and constantly changes, and some software, legacy systems, can stick around for decades, needing ongoing care.
Right. So if bugs are common, how do we even talk about quality? And what about security? That seems huge now.
It is huge. Quality basically means, does the software do what it's supposed to do? Does it meet the requirements and user expectations? Building that quality in from the start is always cheaper than fixing problems later.
But bugs still get through.
They do, despite testing. And with everything connected online, security is paramount. A bug can become a vulnerability. You hear about 0 days.
Yeah, that sounds bad.
It means a vulnerability is found, maybe even exploited by attackers, before the developers have had any chance, 0 days, to fix it. Patching these holes is a constant battle, this ongoing cat and mouse game. And sadly, many systems remain unpatched, leaving doors open.
Scary stuff. Okay, let's peek under the hood slightly. We write code in these languages, but computers only understand binary, right? And
Huh?
how does that translation happen?
Precisely. We use programming languages. Thousands have been invented since the 50s. They range from machine code, which the CPU understands directly, to assembly language, a slightly more readable version, up to the high-level languages like Python or Java we mostly use today.
And those high-level ones are better because...
They're portable, easier to read, easier to write, but they need translating. That happens generally in two ways: compilation or interpretation. Compilation translates the entire program into machine code before you run it, usually faster execution. Interpretation translates it line by line while it's running. Slower, but often more flexible. Compilers also link in external code libraries, and then a system program called a loader gets it ready to run in memory.
Got it. Complex process. Now,
Hmm.
totally different angle.
Hmm.
The law. Software isn't like buying a toaster, legally speaking, is it?
No, it's different because everyone kind of accepts that software often ships with bugs. The legal liability for developers is generally more limited than for, say, a car manufacturer.
Okay. How is it protected then?
Primarily by copyright, which protects the specific expression, the source code itself. That's been the case since the mid-70s. It doesn't protect the underlying idea, though. Sometimes algorithms are kept as trade secrets.
And licenses.
Right, licenses dictate how you can use the software. Proprietary licenses are usually restrictive, while free and open source licenses give you more freedom. Software patents are, well, controversial. They try to protect the functionality, but their history is messy, especially after a big court case in '98, and they're complex and vary by country.
A tangled web, like you said. Okay, pulling it all together. The impact. It's massive, isn't it?
Transformative is probably the word. Software has fundamentally changed, almost everything. How we learn, work, communicate, get information. It's just everywhere in developed countries.
It did just improve old tech. It created new things entirely.
Exactly. It augmented existing technologies, but also enabled totally new ones. The internet itself, smartphones, they wouldn't exist without sophisticated software. Think about creative fields, medicine, science, all revolutionized. Almost every complex device you interact with is controlled by software now.
So, quick recap. We've gone from raw machine code to these incredibly complex apps, seeing how they're built, the constant struggle with bugs and security, how they actually run, the legal side, and just how deeply they've reshaped our world.
It's quite a journey. And when you think about how completely intertwined software is with, well, us now, it leads to a final thought, maybe something for you to ponder.
Okay.
Given this deep integration, what hidden dependencies are we building? What future vulnerabilities might we not even be thinking about yet? Where does exploring this world of software take your thinking next?